Let's say we've been given some kind of process model, a physical process model that we have no control over, but we are tasked with designing a PID controller in order to regulate this process and respond to perturbations and disturbances in our inputs. And so when we're working with PID exclusively, we have 3 tuning parameters for each component of the PID controller that we need to somehow determine what to go with. And figuring out these tuning parameters can be very tricky. And so we use methods such as IMC, the internal model control method, to go about determining what are the best parameters or tuning parameters to go with in our system. And so in this video, I'll work through how we can take a second order process, physical process, and derive what the tuning parameters should be. And so the first thing we'll start out with is G tilde, our internal model. And we're going to need to find Q, which is our IMC controller. And Q is defined to be G tilde minus inverse. And so what that means is G tilde minus is the part of G tilde that is not lag, dead time, or zero order dynamics or positive right-hand plane pulse and or zeros. And so in this case, G tilde minus is equivalent to G tilde. And we're also going to multiply it by a filter to keep our system proper, or semi-proper. And it's just a fancy way of saying that it is a physically realizable controller still in which the degree of the numerator does not exceed the denominator. And so to put this into a math equation, what we're going to find is that Q is equal to the inverse of G tilde, which would be tau 1s plus 1 times tau 2s plus 1 divided by Kp. We're going to multiply this by our filter, which in this case will be 1 over lambda s times plus 1. And lambda is a key tuning parameter of interest for us in the IMC model. And so now that we've defined what our IMC controller is, we now need to find what our standard controller is. So get GC, and GC is equivalent to Q divided by 1 minus Q times G tilde. And this is the standard feedback controller. And so it's pretty much plug and chug and some algebra substitutions. So we've already established that Q is equivalent to tau 1s plus 1 times tau 2s plus 1, quantity divided by Kp times lambda s plus 1. We're going to divide this term by 1 minus tau 1s plus 1, tau 2s plus 1 over Kp times lambda s plus 1. And we multiply this term by G tilde, which we have already been given, which was Kp divided by tau 1s plus 1 times tau 2s plus 1. And we'll note how at this point we can start making some pretty nice cancellations here. All these terms will cancel nicely, and performing some additional algebraic simplifications and rearrangements, we will find that our standard feedback controller GC is equivalent to tau 1 tau 2 s squared plus tau 1 plus tau 2 times s plus 1, quantity divided by Kp, the process gain, times lambda s. And so the key thing to note here is to recall the standard form of a PID controller, in which case GC was equivalent to some kind of controller gain Kc times the quantity tau I, the integral time constant, times tau d, the derivative constant, times s squared plus tau is plus 1, quantity divided by tau is. And so what we do is we will multiply this GC term we've just found by the quantity tau 1 plus tau 2 over tau 1 plus tau 2, so a fancy 1. And after we do that and simplify, what we will ultimately find is that we can rewrite GC in the form tau 1 plus tau 2 divided by your controller gain K, or process gain Kp times lambda, and this quantity is multiplied by tau 1, tau 2, s squared plus quantity tau 1 plus tau 2 times s plus 1. We're going to divide it by tau 1 plus tau 2. And so hopefully we can start to see how the IMC method is telling us what Kc should be equivalent to in terms of our process parameters and the one tuning parameter we have, lambda. And to make this a little more explicit, what we end up finding for a second model process with no dead time is that the tau d tuning parameter in our PID model, based on the IMC method, should be equivalent to tau 1, tau 2 divided by tau 1 plus tau 2. We also see that tau I should be equivalent to, we can see it here, tau I should be equivalent to tau 1 plus tau 2. And finally, our controller gain Kc is very straightforward. We can see that that is equal to tau 1 plus tau 2 over Kp times lambda. And so that is a key takeaway from the IMC method. So the three tuning parameters of our PID controller, the controller gain, the integral time constant, and the derivative constant, we have all just defined explicitly in terms of our model parameters, and these are physical parameters of our system, as well as this additional tuning parameter lambda. And so lambda is the only tuning parameter we need to worry about changing with the IMC-based method in order to trade off between performance and robustness. And so this wraps up how we're able to take a second order process with no dead time, apply the IMC method to obtain the tuning parameters for a PID controller. And so I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.